So, yeah. Now I think it's time to start. I will talk a bit so people will be able to drop in while I start this introduction. I hope everybody can hear me well. And then we should start. So good evening, Australia and Asia. Good afternoon, Europe and Africa. And good morning, America. Very welcome, everybody, to this third WoodRise webinar on fire performance of taller timber buildings. My name is Pierre Landel, and I'm a researcher at the Department of Wood Building Technology at RISE, the Research Institute of Sweden. And we are one of the 24 members of the WoodRise Alliance that started officially 2018, 1 year after the first WoodRise Congress in France. And I will say some few words about this international network. The Alliance and its members have set themselves the objective of contributing to the promotion and enhancement of wood construction, particularly in medium and high-rise buildings, by strengthening their technological collaboration through joint research and innovation projects, and by making their work and results known at events such as international congresses, regional meetings, and webinars like this one. In October this year, from 15th to 19th, we will meet for the third International WoodRise Congress in Kyoto, hosted by the Japan International Association for the Industry of Building and Housing. With the support of this WoodRise Alliance, my colleague Daniel Brandon and I have organized this webinar open to all professionals in different fields. And according to this, the Zoom amount of participants, now we are about 130 participants. And we're working as researchers, but also consultants, product manufacturers, firefighters, insurers, etc. Today, the tallest timber buildings are beyond 85 meters in height and have reached 20 stories. Also, most of the residential and office buildings made of wood are lower than 5 stories maybe. And still, there are challenges at every levels, at all phases of the life of a building. And some of them grow in complexity with the building height on one side and with the will of showing more wooden surfaces on the other side. Wind, acoustic, that's 2 topics from our last webinars, but also seismic, that's 1 topic for our next webinar. And of course, fire safety. Good preparation with up-to-date knowledge is then crucial. So let's now listen to our 4 experts that we have gathered here today, who have been kind to accept to share their latest work and their experiences. They will talk about 15 minutes each, maybe 20, we'll see. I will try to keep the schedule on time so that you will be able to ask questions through the chat function that will be enabled only after the presentation. For your information, this webinar is recorded and will be available online. So now it's a pleasure and an honor to introduce our first guest speaker, David Barber, principal at the consultant company Arup. It's a bit after midnight in Australia, but he's still awake, as you see, and therefore he will answer to your questions directly after his presentation. Many of us are starting now to go back to our offices, at least for maybe some days a week. And if you have one made of wood, I believe it's nice if you can see and touch the timber structure inside, but then the question is, how should a large office space be designed to perform safely in case of fire? That is what we will learn more about. So David, please, the Zoom is yours. You can start to share.
Yeah. Is that coming through okay?
Yeah, it's okay.
Excellent. Well, thank you everybody for joining, and thanks Pierre for the introduction. It's great to see so many people actually tuning in for this, and hopefully the four of us will provide a great set of presentations for you. I'm going to start with an introduction to some of the issues that we're seeing with open plan offices and having exposed mass timber. This presentation will obviously be somewhat of an introduction, aiming for 15 to 20 minutes only, and so I'm just going to quickly, briefly go through what is actually being constructed, some of the issues that we are facing and we know about, some of the issues that we understand and we don't know about, and we need obviously more research on, and then the second part of this will actually just be a quick summary and introduction to the large-scale exposed CLT experiments that currently we're running between Arup, who I am working for, Sarib, a testing and research facility in France, and Imperial College of London. And we'll just provide an introduction to those, which is a good chance to provide introduction to those because we're in the process of actually working on those large-scale experiments at the moment. So what are we seeing? Well, we're seeing a lot of mass timber office buildings. And I think we're seeing these pretty much every part of the world in some ways. That mass timber has certainly seen a significant uptake, certainly in the last 5 years, and that's often to do with sustainability and the desire to have more sustainable buildings. We're seeing obviously a lot of residential, but we are seeing a lot more office construction and the desire to have more offices where there is sustainable construction and a desire to have something which is a little bit different in the marketplace. Timber. They want to know that it's a timber building, but also want to be able to see that timber. And we know that if we have the timber exposed, we are going to have significant extra fuel, and that is going to impact both the heat release and the decay of a fire if it is to occur. We know that with large compartments, we typically don't see flashover behavior. So one of the questions for us as engineers and as anyone who's involved with fire safety of larger spaces and where there is structural timber involved as to what is that behavior. And what we do know is that the fire doesn't just interact with the timber, but the timber actually interacts with and influences the fire. And I think that's one of the most important things that we see when we have exposed structural timber. When we have non-combustible construction, steel or concrete, the fire interacts directly with that structure as such, but we don't sort of have this feedback. With timber, we have a feedback process where the fire interacts with the timber, but actually the timber then influences the fire, and it's that feedback which is incredibly important to understand and to be able to work out, how that impacts buildings, especially high-rise buildings, where we have to design for structural stability, understand, firefighting intervention, and obviously also provide life safety for the occupants. So, that's a brief introduction to what the main issues are when we're looking at mass timber construction, and especially high-rise mass timber construction. So what we've seen over certainly the last 5 or 6 years, and potentially up to the last 10 years, is there's been small scale, room scale, and really in some ways large scale, and this is up to sort of 90 square meters of experimental burns where areas or large areas or significant exposed areas of timber have been involved. And we've now up to over 40 tests where we've got room or large scale compartments. Most of these set up as with residential fire loads, different types of ventilation, sometimes walls exposed, sometimes ceilings exposed, sometimes combinations, often mostly with CLT, sometimes with Glulam and other types of timbers, sometimes in combination. And what we've seen with most of these is very much flashover behavior. The amount of exposed timber has a significant influence on the fire, certainly the growth, and certainly importantly in the decay and the heat release decay. And the type of timber has an impact as well, certainly where we have cross-laminated timber and we have issues with glue line integrity, and we see that in the decay phase. And the importance of that in understanding what happens in that decay phase. We've also seen that, where we want to include the timber, we have to understand that, but also where we want to exclude the timber from the fire, we really need to have reliable encapsulation that prevents that timber from charring and prevents it from becoming, part of the fuel that is actually burning in that fire. So, there has been a lot of very good research, a lot of really good outcomes, and a lot of really useful information for engineers, scientists, and anyone involved in research and application of mass timber when it comes to actual structures and fires. But there is a lot we don't know as well, and I think this is important as well. And this is in some ways, the important part of where we are now and what we need to be doing is that we want to continue to look at what happens in these larger compartments, because part of the issue here is how does the fire actually grow in these spaces. For non-combustible compartments, there's been a reasonably well looked at theory on traveling fires and the impact of fires actually moving through a compartment. Now, when it comes to exposed timber, we don't understand whether that theory still is applicable, and we have some ideas that it may be, but we've also got some significant concerns with that. And also there is quite an issue with how ventilation impacts the actual fire and the spread of the fire, and this whole aspect of the decay as well. Smouldering behavior in the timber is also something which has not been very well studied, and something that we need to understand a lot more of, certainly as engineers and as researchers, to be able to apply the engineering, especially where we are looking at taller buildings. How the thermal penetration occurs through timber, and certainly how it is potentially delayed, and certainly that's very important for vertical load carrying members such as walls or columns. Certainly a very important aspect to understand what occurs, especially in that decay period. Again, external flame projections we have some idea about, or understand where that occurs, but we need certainly more data on that. We certainly need to understand more about firefighting tactics. There is some good work on that, but again, more would be useful. And I think from my point of view, from an engineering point of view, is we really don't have any of the tools and models that we need for larger spaces, and certainly need to understand more about larger spaces to be able to use the tools and models and validate those and make sure they are correct, but also develop the right tools based on the actual fire development that will occur. This diagram some of you may have seen before, but it's a great illustration of where we are, and in some ways what we're designing with, because on the left-hand axis is basically it's a straight ratio of surface area and volume, and on the lower axis is compartment area, and up the side there you'll see that there's plotted all the current timber fire experiments where we've burnt all these rooms and these sort of larger spaces, and as you move sort of down the axis as such and along, you can see some of the larger experiments that have occurred in non-combustible buildings. And this is the largest non-combustible structure that has been had a sort of test experiment within it, and that's at 380 square meters. And we have this issue for both timber and non-combustible compartments, is that what we build is very different to what we test. And there's a certain amount of extrapolation, there's a certain amount of confidence in what we're doing, but certainly from a timber point of view, we know that because we've got this influence of the timber actually influencing the fire, that we need to have a lot better understanding of how smaller scale fires can burn and how they influence the fire dynamics, but we need to have a better understanding before we start to scale up some of these tests to be able to take them into what is actually being designed and built, especially when we don't quite understand the issues between flashover fires and traveling fires. And it's this main issue which is part of the motivation for ourselves working with Sareb and Imperial College to fund these large-scale open plan office experiments, because we are interested primarily in basically into the fire behavior. We want to understand how large areas of exposed CLT influences the fire in these large compartments. You know, what we're also doing with these is there's been previously compartment fires carried out for exactly the same size building with non-combustible ceilings and looking at traveling fires. So we have a baseline where we've got 2 current experiments, 380 square meter building, and understand what the traveling fires were with certain fire loads and certain ventilation. So we can use those as a baseline, and that has become the base for these experiments. And the aim of these is to look at the differences between non-combustible and combustible ceilings and understand that difference of where the timber starts to influence the fire. Also, as part of this, you know, from our point of view, is we didn't want to try to do too much. And I think it's important to understand that, in that a lot of other larger scale experiments have actually taken on a lot of I suppose in some ways goals from the experiment, simply because often they've been related to code changes or been related to getting certain amounts of experiments carried out with trying to get the most out of them. And in some ways, you know, we are very much focused on the fire behavior, and that's important from this, the importance of getting the information out. Quite a little bit of text on the screen, and apologies for that, but I just wanted to quickly squeeze in all the information on the actual building itself. And you'll see on the right hand side here just an image of the structure being constructed, which is actually a spare space at Sareb. That's used to be an area of green area, and there is now a building being constructed on this. The CLT was purchased from Haslaker. We went to a number of different commercially available suppliers and chose one of those. It was certainly, you know, in some ways off the shelf CLT. Within the structure, there was also included 2 Glulam columns. There's actually a single fire protected steel column. In some ways, as a baseline to understand how a steel column would also respond to the same fire. Information there on the fuel load, which was a very well put together continuous wood crib. The opening factor is you know, 1 over opening factor, as I would normally state most of these values, was at 14, and you'll be able to see some of the openings and where they were located on a number of the photos that I'll show in the next part of this presentation. And we also had a number of different thermocouple trees, plate thermometers, photo cameras to be able to capture as much information as we could for the actual structure itself. Putting it together, masonry walls, openings, as I said, openings at the far ends, and both sides had basically similar openings with larger openings at one end. Very, very happy Mohammed today, who in the last couple of days has been awarded his PhD. So congrats to Mohammed, and call out to you. Well done. The wood crib being put together, we had a short area of about 4 meters at one end of a compartment where we didn't have the wood crib, and then the wood crib was continuous all the way down the compartment. And that's just the ignition sequencing just about to start. So that was the building on the morning. Screens, as I said, over a couple of the openings, one over a window and one over a door, to be able to see how the flame projections occurred. CLT in place, and the ignition started at this end. And at this end, we have a larger opening as well. So in this situation we're looking at from this point, we have a very, very well organized wood crib. You know, its primarily aim is to get, you know, a lot of heat and to get that burning very well. And we have quite a lot of ventilation. And the issue here is, even before we started just along this test, there was often a lot of debate around how much ventilation should we have, and is this over ventilated or under ventilated? And of course, part of the process with this is hard to tell. We will actually carry out this experiment and see how we go. And the actual ventilation for this part is exactly the same as the initial X1 tests that were carried out in Poland, and, you know, published information on those. So that was the baseline for starting this test. Just an image as the fire has just started, and obviously starting to get into the wood crib. You can see the exposed CLT, and this is the protected structure which sits in the middle, and allows us to just have the CLT spanning the whole way across. And this is just a steel beam which is protected by mineral wool, and then obviously we want to be able to use that for each of the additional tests later on. Black and white image through, or quite a color enhanced image through the window, and you'll understand why these images were slightly different as we move along. Obviously, plume is just starting to take hold. We've got some ignition starting and some obviously the plume is starting to move down the compartment and just starting to get a little bit of discoloration at the exposed CLT. And as you can see, the wood crib hasn't ignited at all. A few seconds later, we've obviously got significant burning of the timber directly above the fire plume itself, getting the jet starting to move well down the compartment now. Again, as you can see, no ignition of the wood crib as yet as well. A few minutes later, and you can start to see exactly what is going on here. We've obviously got full ignition of the wood crib in this area, full ignition of the CLT in this area, and obviously full ignition in this area as well as the sealing jet has moved along, and we've got the preheating. We've actually got the ignition of the CLT. Remarkably, no actual ignition of the wood crib along here. And watching this live, we had no idea that this was the actual situation. From when we watched the live, our view was that we were getting everything burning at once, and it wasn't until we started to look at this data afterwards and had to look at some of these photos that we were incredibly surprised to see where we had significant ignition on the ceiling, but also you know, a lack of ignition of the wood crib at this point as well. And then, you know, a matter of a minute or so later, we start to get enough, obviously, radiant heat, enough situation in place that we get the wood crib starting to ignite, and we start to get, obviously, the fire starting to spread and move down the compartment. So, you know, this initial stage was, you know, really interesting, just in the fact that we did get that spread along the ceiling, certainly a lot faster than we were expecting. Just as an image back from outside, within sort of 5 minutes of ignition, we pretty much had flashed over the whole compartment. So this is 385 square meter compartment. You can see the wood crib obviously burning, and the whole compartment is completely flashed over, and we have everything burning. We were not expecting that completely. We were expecting there to obviously to be some form of continuous fire, but to get to this point was certainly surprising, but in some ways also interesting from the point of view of how the fire actually developed and continued to grow in this space. A few more minutes further along, we're starting to get, we've got some ways from the opposite side, the ignition has occurred at this right-hand end, and we've got starting to get some decay in the fire at this end, as we're the other end of the building where the fire has moved down to. We've still got, you know, absolute, in some ways, full development of the fire and sort of somewhat flashover conditions at this end, where obviously full flame extension and the fire completely engulfing every part of the structure at that end. Just an image inside showing the wood crib obviously starting to burn away as such, starting to be consumed. The timber column, which was there was two timber columns, one located basically sort of centrally and one located more towards one end. And part of this was to understand, you know, how these columns actually responded. And it's, you know, quite an interesting aspect in itself, just understanding and looking at the timber columns and how they've responded to the fire. And as we progress further into sort of past the 20-25 minute type stage, we started to get dying down of the flaming of the wood crib and a dying down of the flaming of the actual CLT itself, to the point where the temperature started to drop off quite significantly, and obviously we were able to get close enough to be able to start taking some reasonable images inside the actual space as well and see this decay of the fire actually occurring. So just some of the results out of this, I'll just run through these relatively quickly. As an estimate, we think we got around about 120 megawatts as a fire, and this is built up from all the combustibles inside the space. And so, you know, the column 1 and column 2 are just down here. They're very, very small as far as actual contributions to the fire. The CLT is in here. We've got the wood crib. If we sum all those together, we're somewhere in this order, and there is a bound here with regard to assumptions made as to exactly how the burning and combustion efficiency works to give us those ranges. So interesting enough, as far as fire growth goes, we plotted on, you know, the T-squared fires here, the ultra fast, fast and medium type fires. And as you can see, we got very fast growth here. I think we have to be pretty realistic about the fact that we had obviously in some ways a perfect fuel. We had in some ways very, very good openings, which were open right from the beginning of the fire. So we were expecting to get, you know, very good growth with regard to the speed of the fire. That certainly did occur, and it is very evident that when you do have exposed timber and the right ventilation conditions, you will actually get very fast growth. Interesting graph here, just showing the speed of the actual leading edge of the flaming at the CLT and the leading edge of the flaming with the timber crib. And as you can see here, there's a gap where they basically the timber crib, as far as flaming occurs, is always slightly behind that of the CLT. So we're always getting flaming spreading ahead of the CLT, and in that period of time here for minutes where we're basically getting a certain amount of period of growth, and then we're getting both burning the wood crib and the CLT, we are certainly getting to the point where there is always a period where the CLT is ahead of the flames on the CLT are always ahead of those of the wood crib, which in some ways is a little surprising. It's one of those aspects which we considered and we thought about and we thought that may occur, but it was very positive in some ways to be able to affirm that and seeing the test and to be able to see that we are getting that faster spread along the actual exposed ceiling. As far as temperature goes, just a quick snapshot of the temperatures, and this is over a short period of time, just from 5 minutes to about 6.5 minutes. This is along the centerliner of the compartment, and as you can see, that's sort of just snapshots of some of the flaming that's occurring at the same time. And you can see the sort of, the temperatures moving through the compartment. One of the interesting aspects, which is in some ways validation of some of the research that has occurred, is that you will see along here and at the top that the peak temperatures are not right at the top of the actual space. They're actually slightly below the ceiling. And we are getting, and in some ways verifying this, and it'll be interesting to see when we carry out the second test if we get exactly the same results, but we are getting temperatures that are peak temperatures below the actual exposed CLT. They're not directly at the CLT. And this can be seen further in this set of graphs, which is simply plots of the temperature over time at 3 different locations. One just slightly into where the wood crib started, one about mid-length along the compartment, and one towards the end. And this is those 3 graphs of location of the temperatures. And it all points that the peak temperatures are at a height of 2.4 meters, not at 3 meters. So those peak temperatures occur slightly, not at the top of the compartment, but actually during, in some ways, in sort of the mid-range of the compartment, or just slightly below this layer that occurs where, and it's partly driven by the fact we're getting so much pyrolysis gases coming off of the CLT. We have a situation where we don't have enough ventilation in that space, and this is one of those aspects we looked at and realized that, even though it was a very well ventilated compartment, there certainly wasn't enough ventilation, and we are getting a situation where the temperatures are peaking in an area which is slightly below. Another interesting aspect looking at this is the fact that at one end of the compartment, we've got quite a reasonable separation of temperatures between, 1 meter height and 3 meter height. And there's in some ways, kind of 2-zone approach. At the far end of the compartment, where we're down at this end of the ignition and flames move in this direction, that separation doesn't really occur. And we've got fairly kind of consistent temperatures across the whole height from 1 meter to 3 meter. Decay rates are similar, but that separation in temperatures is quite different along the actual compartment. So what's next, just to wrap this up, we're in the process of writing a paper which we'll publish and we'll put through to be published, which will provide basically results on of what we've seen so far of the first experiment, and then we're looking at separate papers to dig into a little bit more detail on some of those other issues that we're wanting to sort of at least explore. We're in the process of setting up for our second experiment, which will occur in the next 2 weeks. A lot of work on the sides as we get that ready and get that prepared, and we're basically having exactly the same situation but with half the ventilation. So it's primarily knocking out every second window or every second door as such, and having basically exactly the ventilation. Everything else is identical. So it's all about understanding the impact of the ventilation on those actual fire dynamics and be able to compare the two. At the moment, this is supporting 2 PhDs in Imperial. We are considering a third test and trying to understand what that will consist of and what will be important for that. And I think that will depend on what comes out of the second test as to how much we need that third test and what will be the variations with that. There's certainly a lot of work to digest, and we're considering continuing to work on that, and we will be obviously for quite a period of time as we move forward. So just finally, special thanks to all the team. Obviously, there's a significant team of people working on this at the moment, all of those at Arup, everyone at Sareb and Imperial, and our separate steering group as well. So thank you for that, and yeah, happy to take a few questions in the time that's available.
Thank you very much, David, for this presentation. Very good. And now, so I just opened the chat for maybe around 10 minutes. So if people want to start to write a question, let's see if it works. I'm sure there are some participants that want to ask a question to you. Then you will be able to choose if you want to go to bed or continue listening. And but please try to write as short question as possible. Let's see. I hope the chat is working. Yeah, it's working. Do you see the question?
Yes, I do.
Yeah, then you can just read it.
So the first question is, at what temperature would the CLT ignite via the pilot ignition from the crib below? So some of these I'm just going to have to give you estimates on because I don't actually have all that data in front of me, and so it will be in the published paper. So some of these, sorry, I'm going to have to be able to give you an estimate, but it was within a minute or so. And it depends exactly what we consider to be ignition. From the point of view of being able to see, I suppose, at least some flame extension along the CLT and see sort of charring from the imagery, certainly within 2 minutes that had occurred, and it probably has occurred within I suppose a minute or two of the actual ignition. There was obviously a small period of time before the flames actually grew to the point where we actually had a proper fire plume. So, but certainly from the point of ignition to the actual point that we consider that the flames reached the end of the compartment, that occurred within around 5 minutes. So that's another way to be able to think about that.
And there's another question from Germaine Muller.
Yeah, just didn't hear clearly, but did you say that the flashover occurred in 5 minutes? Yes, it did. We did talk before the test as to what we thought would be flashover time, and we were generally in the order of sort of 5 to 10 minutes, 12 minutes. It occurred right at the bottom end of that range. And so, yeah, but it was close to 5 minutes that we actually had the point where that we considered everything had reached, I suppose, a flashover point.
You mentioned that you were quite surprised that you get actually a flashover, but do you know, do you have some clue of why it happens here? Is it because of the fuel or the CLT or?
Yeah, I think the best way to think about that is that there was two other tests in basically an identical compartment with a non-combustible sealing, and when we look at the results from those, we actually had a traveling fire. So we never got a flashover. We actually had a fire which grew and then moved along and through the compartment, and there's published papers on those, and it's useful to have a look at those and look at the results. And I think using that as the baseline, when we saw the results from these tests, we got a situation where everything was burning, and obviously the difference in this is the CLT, having the exposed CLT, because it was for this test, it was the only difference between the first test, X1 and X2, was simply the fact that there was a combustible sealing.
Now we have more questions. Let's see. Maybe you want to pick some of them. Now it's going a bit faster. Something, I don't know. Yeah,
Yeah,
you use oh, please.
I was going to say, sorry, size of the compartment, 385 square meters. That's easy one to do. 35 meters in length, if that's way to think about that. Yeah, 385. Thank you. Another one here. How does the time to flashover compare to a previous test, the non-combustible compartment of the same size? I don't know the exact data on that, and I would have to go back and have a look at the papers. But the X1 and X2 tests, I don't actually physically think reached a physical flashover. So they actually had more of a traveling fire. So I don't think we got to that situation. Hopefully, one of the people involved in either Mohammed or Panos or Ogle may comment on that and be able to just put in the chat to make sure I was correct about that. But I'm pretty sure they actually didn't reach a flashover. So we have two different outcomes for a similar, an identical compartment size, with the only difference being the exposed CLT.
I choose to close the chat because we have to keep the time on schedule. So, but maybe 1 or 2 minutes more. So if there is a question about glue, which is very important.
Yeah, so correct, Haslaka was using MUF glue, and we wanted to confirm, the glue line integrity that occurred with their panels, which they've got testing to confirm that. We did intentionally use a CLT with glue line integrity because we wanted to take out the uncertainty around the issues we've seen with other fire experiments with, char fall off and issues with glue line integrity with CLT and issues of regrowth and those sort of aspects. And from our point of view, when we're designing larger spaces where we are using exposed timber, because of that uncertainty and because that influences the decay, we want to be able to, as designers, take out that uncertainty. So we chose, as a design team and as a project team, to use CLT panels where we knew we would have a certain type of behavior with regard to fire exposure, and part of that was to take out one of the variables and take out one of the unknowns, and that's the issues of glue line integrity. And so, as designers, we can choose to do that, and we can choose to specify that. So it's a lot easier to design a space where you have one of the significant unknowns and significant variabilities if you can actually take that out of the equation, and therefore makes the process of design somewhat easier. So that was the decision making we went through with that.
Mm-hmm. Okay, I think we have to move on. And thank you again, David, and feel free to continue this interesting webinar. Now it's time to listen to our 3 next speakers in a row. So with the next one, we will continue to learn more from recent compartment fire experiments, but now on the place where we spend most of the time, our homes. And this presentation will be given by Daniel Brandon, a senior researcher in fire dynamics and a colleague of mine at WoodRise in Sweden. So please, Daniel, you might start to talk and to share your presentation. Let's see, I see you. Mm-hmm.
Yes, can you hear me?
Yes.
Good, and can you see the screen?
Yeah, but I see this in, in this presentation view or speaker view with the next slide. So this you have to click something.
Yes, it should be fine now, right?
Looks great.
Good, thanks. Thank you, Pierre, for the introduction. Yes, this presentation will be about fire design of exposed mass timber, and I will focus on apartments, and that is in relation to the previous presentation. We did aim to involve, to get knowledge for office buildings as well, but the focus of this presentation is apartments. I am presenting results of a project, and I present on behalf of the whole project team. The project that I present the results from is called Fire Safe Implementation of Visible Mass Timber in Tall Buildings. And that project is funded by the US Department of Agriculture, US Forest Service. The project manager is the American Wood Council, and we are at WoodRise the contractor. We have material sponsors, which are Katara, KLH, Henkel, USG Knauf, Boise Cascade. We got additional support from Softwood Export Council for transporting products from the US to Sweden. We also get some financial support from Brandforsk, which is the Swedish Fire Research Association. And they paid for additional measurements outside of the compartment and analysis of that. On this website, we publish all information. At the moment, we just have the summary report. The final report is soon coming, and we will have some other reports, of which one will be about predictive modeling, and another will be about repairing of fire damaged CLT, a case study of repairing. To go to the reason why we did these tests, I have to go to some background information. Here I mentioned the results of a project led by the NFPA, and the contractors in that study were NRC Canada, NIST, and WoodRise. The tests were done at NIST, and also this photo was taken at NIST. Here you see two compartment configurations. I'll just discuss the one on the left in this slide. We have a heat release rate curve on the left that corresponds to this configuration with all surfaces of CLT protected. And I'm happy that David did give an introduction of the issues there. There are some issues with, I guess there were some unknowns regarding the energy contribution of timber, the way it interacts with the fire. And therefore, we had a baseline test where all surfaces were protected. And this is the combustion rate corresponding to that fire. In this configuration, there were also 3 other tests in this study. And what we saw is that you get an increase of combustion rate at some point during the fire, at several points, while we know that the combustible fuel on the floor is starting to burn out. We did see an increase of heat release rate, and that needs an explanation because it's not the fuel on the floor. In these cases, it was glue line integrity failure, and that I guess the aim from that moment was to actually avoid glue line integrity failure, like in the David presented. They did the same thing. So we had several compartment tests with CLT that did not show glue line integrity failure. And you can imagine that if these increases of heat release rate are not there, you can expect a significantly different fire and a more improved fire scenario. By now, there are some standard tests in the US and in Canada. There is a requirement for CLT to withstand full-scale compartment fire test without reheating of the fire. And that is required in the ANSI APA PRG 320 since 2018. In Europe, there we can expect a standard test in one of the annexes of the next Eurocode 5. And both of these tests aim to avoid glue line integrity failure. And that would change the interaction of the timber with the compartment fire significantly. And that's why we conducted these compartment fire tests. The main objectives are design and perform 5 compartment fire tests with PRG 320 2018 compliant CLT. So this test, this standard has a test where that aims to rule out glue line integrity failure. We perform these compartment fire tests with a varying amount of exposed mass timber areas. And we assess these fires against a performance criterion where a fire should decay from the onset of decay. It should decay until at least 4 hours after ignition. And this assessment criterion was also used for previous changes in building codes. And therefore we thought it is good to implement it in our research as well. The project also had secondary objectives. I will not talk in detail about those, I'll just mention them. We have predictive modeling, which has been really helpful to design the compartments. We have information of intersections between mass timber members, the performance of different solutions of intersections, intersection details. We recorded facade exposure and compared it to standard tests all over the world. And we had a case study of repairing CLT after a fire. And this last point is still ongoing, but the rest is finished. Just one slide back. So the main objective is to design and perform compartment fire tests. The first step of this is to design the compartments. In this study, we aim to get a severe but realistic scenario. And we know, as David already said, ventilation is a very important parameter. And for this study, for this probabilistic study, we did a survey of which opening factors, which ventilation openings you could expect during a fire. And we looked at modern multi-story buildings made of all kinds of materials, but also specifically an additional database on timber buildings as well. And we got the distribution of opening factors that we could expect. In the probabilistic analysis, I cannot go into detail in the time that I have today. We aim to get a higher percentile expected damage in relation to the range of modeled fire scenarios, and we used 200,000 modeled fire scenarios using a relatively simple model. And using this probabilistic analysis, we aim to select a scenario that would lead to relatively severe damage. That analysis resulted in a smaller opening factor. We also included a test with a larger opening factor, which would correspond much more to open office spaces in the database. So the purple distribution of opening factors corresponds to office spaces, and we can see that the range is much higher than the smaller openings we have seen in apartment buildings. One thing that could be noted is the orange distribution is timber buildings in general. We have seen larger openings in multi-story timber buildings. These are the configurations of the tests. There were several different areas of the structure protected and different areas exposed. In all tests, we had an exposed CLT ceiling and an exposed beam, a Glulam beam underneath the ceiling. We had varying numbers of layers of gypsum boards, and the one test that we did design in advance is test 1. All subsequent tests were designed during the test series based on these three things: the performance of the previous test, modeling predictions, which has been quite useful and reasonably accurate. Then also discussions with the steering group have led to the decision of which configuration had to be tested. Here you see some pictures of the construction phase. We covered the compartment after the ceiling was the ceiling was finished, and this cover would only leave before the test. Here you see the fuel load in the room. What you don't see is some wood cribs that are actually implemented inside some furniture. So in this sofa, these drawers, there is wood cribs, the cabinet, and also underneath the table to simulate a heavier table and chairs. In total, 40% of the fuel load was wood crib. Here we see all fires from flashover, from the start of flashover. Test 4 decayed relatively quickly. That is due to high burning rate, but also a lot of cooling effect due to larger openings, which does correspond to our data from office spaces. Then we have test 1, where the ceiling and the beam was exposed, and there after 22 minutes of flashover, the decay started, and that took 6 to 9 minutes longer for test 2, 3, and 5, which had significantly more surface area exposed. As a reference, I included the test done by at NIST, and these videos are also made by NIST. And this compartment, which I discussed before, had CLT that is not compliant with PRG 320, and fire bond line failure was seen in 2 layers in this test. Now we go to the end of the test, and we see that test 1, 2, 4, and 5 decayed. They decayed until the 4-hour mark. In test 3, we had reheating of the walls, and despite the similarity between test 3 and 5, there was a different outcome. The significant difference between test 3 and 5 is that in test 3 we had exposed wall corners, exposed walls meeting intersecting at a corner, and in test 5 we didn't have that. And in this corner we saw, in test 3, in the bottom of the corner we saw an increased damage. In test 5 that was not the case, and all corners in test 5 had at least one surface of gypsum board protected wall. And as a reference, I included this previous test with CLT that doesn't comply with the current PRG 320 standards. And you can see that it has a significantly different outcome. Yes, just to emphasize that there was a significant difference in terms of where the CLT surfaces were, and we have seen a lot of signs of the walls in the corner in the bottom re-radiating to each other in test 3. And that wasn't the case in any test where at least one wall was protected in a corner. Some results: we determined the mass loss of the floor. We determined also the mass loss of the compartment itself, everything except for the floor. And the idea was to get information of the mass loss of the fuel load on the floor and the mass loss of the structure separately. We calculated the heat release rates based on the heat of combustion of the fuel, and that is shown here. We also measured the internal conditions with multiple devices, thermocouples, but also plate thermometers. And the plate thermometer temperature is often used as a proxy for thermal radiation, which is actually the most significant mode of heat transfer at fire temperatures. In this graph, you see the red dashed line included. That's our temperature criteria, temperature criterion at 4 hours. And I haven't discussed it here in this presentation. It is more thoroughly discussed in the report. We wanted to have the temperatures under 300 degrees at 4 hours, and that didn't work for test 3, but it did work for the other tests. Here you see the charring depth of in the ceiling after all tests. It should be noted that the char depth in the bottom of the compartment was generally higher. However, because the ceiling was exposed in all tests, it allowed for a nice comparison. This is actually the best comparison we have when it comes to char depth of all fire tests. And we see that increasing the surface area of exposed mass timber actually leads to an increase of char depth. And for reference, I also included char depth that has to be calculated in the US for 2-hour fire resistance testing. That was a very short, a very brief selection of the results. And the conclusions related to the results that I showed today is the fire in the compartment with the ceiling exposed and walls protected with 2 layers of type X gypsum boards decayed at least up to 4 hours after ignition. Fires in compartments with significant areas of additional exposed wall surfaces decayed at least up to 4 hours after ignition, with one exception, and that was test 3, where we had exposed wall surfaces intersecting in multiple corners. And there we saw an increased damage in the bottom of the corners. Before I finalize this presentation, I would just want to mention that there is a report coming up of the predictive modeling. We did a priori modeling before the tests. That is very similar to what you see here. We just made a slight change in the decay phase, but also everything is included in the report. The model is a zone model, and it can be used to predict the gas temperatures, the surface temperatures, the fire duration, also the temperatures inside the CLT, and also the temperatures behind the gypsum board to predict charring behind the gypsum boards. Eventually, the aim is to use this also for structural calculations. And then finally, we also do a case study on repairing exposed CLT, but due to logistical issues that is actually ongoing right now. And these reports will also be available on our project website shown here. Well, thank you for listening. I think the questions would come after the last
yeah, exactly. Yeah. Thanks a lot, Daniel, for this great presentation. And yeah, as you mentioned, so I encourage everybody, all participants, to keep in mind their questions to Daniel, and we will be able to write them after the last speaker. So now we will listen to Christian Dagenet, a lead scientist in building systems at FP Innovations and also invited professor at Université Laval in Quebec. And he will take us now on a time journey of 15 years about fire safety, performance, and regulations. So please, Christian, you have also about 15, 20 minutes.
Perfect, thank you.
Let's see, you can start to share.
Yep, not sure, just a second.
Let's see.
Oh, okay, got it.
Looks good, great.
Right. Okay, thank you. So indeed today I'm gonna, as Pierre mentioned, it's gonna be a time journey across the different work related to fire performance of timber systems. So we will review some past, current, and future work on fire safety. So just to give you a timeline, I would say, past work relate to what has been done at least 5 years ago, which is pretty much fairly recent and the most. Some current work that is from the past 5 years up to now, and future work. So what will be some new research needs and what we envision as the next step. So just to start, to differentiate with the types of wood frame systems, of timber systems, I would say. So we have the wood frame construction that has different names across other countries. In North America, this system is the dominant one in residential buildings. From market studies, we know that from 1 to 4 stories, this system is about 97% of the market shares in Canada and 94% in US. So largely dominated by wood frame construction. And for the 5 and 6 stories, we have a strong increase. We had a code change in 2015 in Canada to allow 5 and 6 stories. So we have seen that from that code change, we were from 26% and now to 65%. So we have a strong increase in that area as well with that type of system. What is important to understand also is that there's numerous products available for that type of system. It's not just timber. So we have the prefabricated wood I-joists, we have the wood trusses, and as well as structural composite lumber. In there, there has been a long list of tested assemblies, either wall or floors that has been exposed to standard fire exposure. I'm putting the ISO 834 as the reference, but other countries have other standard for fire resistance. There has been some amount of compartment fires to assess the fire dynamics in this kind of construction. And all of these tests has allowed us to evaluate the effects of various design parameters. Wood frame construction is not necessarily a very complicated system, but we wanted to know what's the effect of the gypsum board. North America would be type X, European would be type F, or there could be some other classification of gypsum board. The test has allowed us to also understand what's the effect of, for instance, resilient channels on the performance of the gypsum boards, and also the insulation, namely for wall assemblies where the insulation would play a significant role. From all these tests, what we know is that wood frame can provide significant fire resistance way beyond 2 hours. So there has been a number of tests to demonstrate those. And essentially, manufacturers of wood frame assemblies and association have all of the tested assemblies available to designers. So it's just a matter of asking, and they will be more than pleased to share the info with you. All of these tests has allowed to develop a number of calculation methods over the years. In North America, we have what we call the component additive method. This method is limited for now is limited to 90 minutes of fire resistance. And essentially it consists at additioning the contribution of the various components. So you add a time assigned to a gypsum board, you add the time assigned to the wood joists or the wood studs, and a time contribution for the installation, and the sum will give you the fire resistance. So it's really straightforward and easy to use. There also has been a model developed in Eurocode 5 that has been published in 2004. And section 5 specifically deals with wood frame. And the method there is limited to an hour, to 60 minutes. And it allows you to determine the load-bearing function or separating function. So the Eurocode 5 has quite a bit more sophisticated approach so that you can really evaluate whether the load-bearing or separating function is needed. The other type of system that I'm presenting here is the post and beam construction. So perhaps more of the traditional system that we used to see, and also mass timber, which is more of the trend now related to timber construction, and especially in the case of tall buildings, that would be mass timber construction. So the difference is that the main difference is that the elements are of large cross section, and due to their bigger size, they have an inherent fire resistance, and that has been proven throughout the years from many old buildings that has been constructed. So there's a few products available in that category as well. So we have the sawn timber, which as of today, we see less and less because we now see more of the engineered wood, like the Glulam, the glue-laminated timber. We have the structural composite lumber, and also CLT, as we've seen in the two previous presentation. There were also, this type of system is also using connection more, I would say more of traditional fasteners. So we've seen steel and iron caps as you see in the picture at the bottom right. We have seen wood pegs, dovetail connections, bolts, dowel, rivets. So all of these, I would say old school connection types has been used in this category. And again, similar to wood frame, these products has been tested for standard fire exposure. There has been some compartment fires to assess the fire dynamics and the exposed surfaces. David and Daniel just presented the latest info. And all of these tests throughout the years has allowed us to develop a lot of parameters. Obviously, the first one that comes to mind is the charring rate. And there also has been a long list of studies to assess what is the effect of the density, the moisture content, the heat level exposure, and as well as the thermal gradient inside the timber once it's being charred. There has been some work to develop some thermal properties. So these are mostly used in advanced modeling, like finite element modeling, but at least there has been some work to derive those properties, which are not really obvious because at 300 degrees Celsius, everything is consumed. So it's difficult to develop properties beyond that. We have also a long list of combustion properties, ignition temperature, ignition time, pyrolysis, mass loss, heat of combustion, smoke, different other types that could, for instance, come out from the cone calorimeter test. And there has been some tests on connections. That goes back to what I was saying. Most of the tests so far has been done on old school fasteners, so bolts and dowels, and unfortunately to relatively short duration, from 20 to 45, 60 minutes. Nevertheless, all of the tests have demonstrated that these assemblies and systems could withstand and provide fire resistance beyond 2 hours. So that can easily be used for taller buildings, and it's easy to calculate. However, from the test, we found that also that connections may be the weak point. So there's some need to continue to work in that area. I'll come back a little bit later. So for the post and beam mass timber construction calculation, there has been some calculation method also developed over the years. most of them are similar to what was done to wood frame or has been adjusted to account for the larger cross sections of these elements. So in North America, we have had the what we call the TT-Lee equations that from NRC that came up in 1977. And these were applicable to glulam and timber elements. In Canada, we recently had a new calculation method in our wood design standard, CSA 086. And we also have some generic char rates, whether it's timber, glulam, CLT, and we have additional times for the contribution of gypsum board. So whether the assembly is protected by 1 or 2 layer of gypsum boards, we can add a few minutes or significant more minutes to the fire resistance of the unprotected element. In the US is a similar approach. So we do have the, I would say, the old calculation method from 77. However, they have a more modern approach. So the National Design Specification and Technical Report 10 propose a charring method for timber element exposed to the standard fire. So the 086 in Canada is largely inspired by that method. In the US, however, it's limited to 2 hours. And again, just like in Canada, it provides generic charring rates as well as time contribution for the use of gypsum boards. In Europe, in the Eurocode 5 2004, similar approach. So also it's applicable to pretty much any types of timber building elements, except CLT, not yet implemented. They have generic charring rates based on the type of products and also the effect of the gypsum boards, how to calculate it with a more, I would say, advanced or sophisticated manner. They have one great asset they have in the Eurocode 5 is that they also have provisions for connections. However, the method is limited to 1 hour. And they also have provisions for advanced modeling, like the thermal properties I was mentioning. They have implemented them in Eurocode 5 so that designers can actually use them to develop some advanced modeling. So with the current, so those were where we came from and what we know. And now what we're currently working on for the past few years and most likely a few years after is to continue to work and study the fire performance of different other types of products and systems. There are and will still be new materials and systems being developed. So we need to know essentially all of their fire performance, whether it's combustion properties, fire resistance, flame spread, whatever. So there will be always need to evaluate these new materials. We know there's also a trend to use new insulation materials like bio-based insulation, straw bale, I would say more greener elements. And so we need to also evaluate those. And we're seeing a bit more use of other types of membrane protection, so something else than the traditional gypsum board. 2 examples here are the fiber cement boards and the magnesium oxide boards. And so how do they perform in fire on a wood frame assembly? These still need to be assessed if we want to document them into a more generic manner. With the push to 5- and 6-story wood frame construction, we also need new lateral load resisting systems. One of the examples is the mid-ply shear walls that FP Innovations developed a few years ago. And so this type of shear wall, as you see at the bottom right, allows the shear membrane to be solicited in double shear, so that increases its capacity. So it's useful for higher buildings or wood frame buildings that would otherwise be in high seismic areas. So we changed the configuration of the wall, so we need to focus and test the assembly to assess its performance. What we're also seeing in the market is the change in the wall assemblies to meet various types of demands. The change that we're mostly seeing are the needs for energy efficient exterior walls. So something that would either be thicker cavities, more insulation, or insulation outside of the wall as opposed to inside. So that changes the overall performance and also needs to be assessed as to what is the effect from moving one component elsewhere across the wall assembly. We also see high capacity walls for compression loads. So there could be staggered stud, so not a standard one row of stud. We could see walls with engineered wood-based stud, like the structural composite lumber, which has not been tested per se. So we need to know, is there a difference? And some walls with enhanced acoustic performance. So maybe now new assemblies that we would see with gypsum membrane or other types of membrane that would be on it, but that are not necessarily the traditional gypsum board and resilient channel. And so from all of these recent trends, these has led to refinement of existing methods. I would say for now, the most change will be coming in the Eurocode 5 that should come out somewhere between 2025 or 2027. But there will be a significant change in the in this method, and the next Joachim will present a bit more in details later. But one of the major changes is you will have thermal properties for insulation materials and gypsum board, which were not in it first. There is a whole review of the effect of insulation and the onset of charring on wood studs for the wood frame construction, and I would say, and many more. And as I mentioned, Joachim will present those later on. In the US, there has been also a industry standard. When I did the slide, I was saying coming out soon by American Wood Council, but I've been advised by AWC that the industry standard is now published, so you can download it through their website. And so this has changed slightly a little bit the design method. And for Canada, the current method for calculating timber is limited only to large timber elements. So there was a need to revise whether the method fits for wood frame assemblies, and that review has been complicated and will be submitted soon for some changes. Also, current work on CLT. We got the comment previously by David's presentation, but the adhesive performance on CLT. It's not necessarily a new issue. I would say it's kind of a past/current work. The adhesive performance has somehow been resolved, at least in North America, since 2018. And I know there's some push in other countries, including Europe, to get rid of the adhesive delamination, I would say. So this is still ongoing, although most likely finished. Mechanically laminated timber, that is kind of another type of category, mass timber category that would fit in there. There's various products available. The more traditional one would be the nail laminated timber. There has been some tests to evaluate the charring rate and also the effect of gaps, as you see at the top right picture. So if the boards are separated by a few millimeters, what is the effect on the overall flaming inside this gap and increased charring? There's another product available also that is the dowel laminated timber, and we also start seeing the screw laminated timber. So all of these require to review whether the systems still fit within the current model, or vice versa, is the current model fits to this system. Also on connections, we're seeing now more testing on innovative fasteners like the self-tapping screws, but we're also seeing more, I would say, modern types of systems like beam column assemblies, embedded bearing connections. And so we're moving away from the traditional bolts and dowels and going to what is more of the modern types of mass timber systems. And we're also seeing more calculation methods and tests beyond 60 minutes. So ideally, results that could be used for tall buildings. And lastly, encapsulation methods. We have pretty much good information on single and double assemblies for gypsum board, but now we're starting to see triple layers of gypsum board to improve the overall performance and delay significantly the potential contribution of mass timber in a fire. Also current work, compartment fires. So David and Danielle has presented some of the ongoing or almost finished compartment fires, but there has been some significantly more testing in the past few years that were not necessarily presented in this webinar. And also we're still doing some testing to see the effect of non-delaminating products. So most of the previous tests on compartment fires were, as one commenter pointed out, was made with CLT that were exhibiting delamination. And now we want to see what's the effect of the non-delaminating products. Also, fire safety engineering, this is ongoing. The important thing is, for now, is to see whether the general principles of fire safety engineering are applicable to timber construction. David alluded to those, that there's a number of uncertainties that as an engineer you want to ensure or get rid of. So what's need to be done to make sure that we get these uncertainties out? One of them would be to continue to develop thermostructural models. For now, what we've seen is there usually sequential coupling. So then one will do the thermal model to see what's the heat transfer inside an element, and then use these results and put them into a structural model. So it's the two-way coupling is different. It's a more sophisticated, but the sequential for now is reasonable. What we've seen also is that these models are usually for single elements like a column or a beam, with some modeling showing the connection performance at the same time. So as future work, where are we going and where should we going, at least from my opinion, it's to still continue to focus on fire safety engineering. So all of the general principles, make sure that we remove one by one all of the uncertainties and provide the relevant data and test data and confidence to designers to use these principles with timber construction. One of the few missing points are the fire dynamics in large open space. So David is already addressing those through the ARUP research. But the other more, I would say, simplest things would be to review the charring rate and thermal properties, but for other exposure than the standard fires. Are they that different? Could they still be used or modified based on whatever parameters? So these needs to be reviewed. And also all the timber contribution in advanced modeling, namely the CFD. So those doing advanced modeling, how can I account for timber contribution in a CFD modeling and to remove any conservatism? But lastly, the most important one would be the shift to performance-based design, essentially to let go of the combustibility classification. Materials will still remain combustible, non-combustible, difficult combustible, but at least going through a performance-based design will allow all materials to play on the same level and reviewed and engineered based on advanced principles. Also, future work is again the modeling. I would say now the two-way coupling, so that at every time step, thermal and structural talks to each other. And also something that we could overlook at more of a system approach as opposed to an element approach. So how is a beam column interacting together, or maybe a full compartment that could be model. And also modern connections. As I mentioned, there are some tests demonstrating the performance of traditional fasteners, bolts and dowels, but now we want to know more of the modern types of system.
Please, Christian, we are running out of time.
Yep, that is my last slide, Pierre.
Great.
The last few items would be rehabilitation post-fire. So what happens through after a sprinkler discharge with respect to water damage and structural rehabilitation? So Daniel is looking at one of these items already at RISE. We need more tests on connections, but with modern connection types, as you can see on these pictures. Hybrid systems. There has been a number of tests on concrete timber, but we're also seeing more and more of steel timber. And how about other materials? I'm seeing aluminum here, but there could be some others depending where you are on the country, that other materials could be interested to mix with timber. And lastly, still of very interest these days is fire safety of facade. So what test method should we use? There's a number of those already in place anyway in many countries. And what would be the risk mitigation strategies for those facade? So in conclusion, I'll stick just to the main point, but wood frame construction is very well understood. Post and beam construction and mass timber is relatively well understood for now. But there's many key aspects that are still misunderstood by the design communities, whether it's building officials, firefighters, insurance companies. And performance-based design is gaining popularity, and wood design, timber design needs to fit into performance-based design as with any other material. So we need to develop all of not develop all, but what's left to develop in terms of supporting that approach. Thank you.
Great. Yep, thank you very much, Christian, for this instructive journey. And to everybody, so please wait a bit for writing your questions to Christian. And finally, so I would like to introduce a former colleague of mine, Joachim Schmidt. He is now working as a senior researcher at the University of ETH Zurich in Switzerland, but also as a fire safety engineer in fire dynamic for Ignis. And Joachim is much involved in the standardization of design codes. And today he will share with us some valuable details from the new Eurocodes on fire design for timber structures to come around 2025, I think. So please, Joachim, you may start.
Thank you, Pierre, for the nice introduction. Yes, so I was asked to present something with respect to compartment fire design in Eurocode. And I took also the opportunity to show you the current status, a comparison with the actual version and the coming version. And unfortunately, I have to inform you that we have to expect, or we have to wait some more years. So the Eurocode in its next generation is to be confirmed and approved 2025 to 2027. So let's wait some more years. But I think the draft is spreading, and I think why not use it by now? So let's start. In my presentation, I will go through the evolution of Eurocode and will show you some of the differences. I will give you a design model overview when it comes to fire design, and we will have a look on what's available and valid also for timber. And then we will have a deeper look into the consideration of structural timber. Why should we do that, and how can we do it? And I will give you some, let's say, insights on the physics and how we want to apply that. And close to the end, we will then have some application examples. I will not have fancy videos shown. I will just have some graphs, and you will see some equations. You will probably, let's say, try to understand, and they are so simple that they are useful for the future design, and you should keep in mind. I will conclude in one or two slides then. So when we have a look in Eurocodes about fire design, and we want to know more about the structural fuel load, fuel by structural timber, then we will find in Eurocode 1, which should be our first, let's say, knowledge point, that we do not have anything there. It said there, please consider fuel if it's the interior or the structure. However, also Eurocode 5, same sentence, just a different release date. There's no guidance given about how the fuel by structural timber, or the structural fuel, as I call it, can be calculated. So the only option you have is you consult guidance documents, books for fire in general, or quite well available information about how timber reacts and behaves in fire. And there is still a web page open for the cost action, the previous one now finalized already for 2 years, but content will be extended and also transferred to another web page, which is called Fire Safe Use of Wood. So I will invite you to check sometimes where when and where we will do some updates. I would also refer to a Canadian handbook, which is quite useful, and some very recent research done in UK with the STA group. Now, evolution of Eurocodes, I told you, Eurocode is a very good, let's say, tool, but it should solve everything. And this is, in fact, at the moment, expected from Eurocode. You should deal with timber frames, you should deal with post beam construction in rectangular shape, irregular shape, and also CLT. However, to be honest, CLT was not really included in Eurocode, and partly rules have been, let's say, incorrectly used and applied on CLT. But this is now to be solved and becoming much better in the next version of Eurocode. What we will not do, and will Eurocode never deliver, is, let's say, clear rules how to build a skyscraper out of wood, because for that you need special expertise, which is also valid for complex and larger structures. But guidance on, let's say, 80% of the buildings that should be implemented in Eurocode. And that was also the task of the project team where I was a member of when we did this writing of the Eurocode draft, which exists now. Having a look at that and comparing it to the old version. So 2004 is the old version, and 2025, I'm quite an optimist, that is the new version. So looking at the page numbers, I could identify some interesting spots here. And that is one, the mechanical resistance. It grows because we have now more, let's say, products involved, CLT, quite a large chapter, but also more small elements, I-joists, which have not been involved or incorporated there in the 2004 versions, that is now covered. On the other hand, and that will be content of my presentation today, the next slides, is non-standard fire design, which means that not everything is invalid for non-standard fire design, but most of the design is expected also in the future to be done for standard fire. For example, detailing will be an issue for any of the design. And also external flaming, which is a new chapter, is probably something everybody will be interested of. Now, having said that, I would like to point out that Eurocode is just one piece of the full picture you have to consider, or an engineer should use and let's say take into account when designing a building or doing a member verification. There's still testing around, and more importantly, probably there's still these building regulations you have to follow, and where you will find proper guidance, hopefully. And if not, you can consult similar, let's say, papers and manuals given by the associations of timber industry in your country or also abroad. Now, reporting from the team of the project team dealing with the draft of Eurocode. So we were given the old Eurocode with some tools, and we were also, let's say, addressed by wishes. Everything should be more accurate, everything should be more easy, and all models should be also fit for the future. So it was a difficult task to do that, but we did our best in rearranging tools, in putting more tools together, and these tools can be used in the future by engineers to answer questions. Not all of them, but more and more. And I think they are good tools, and I'm very happy to present Eurocode very soon to you. And please send comments to VG4 if you are not happy and see some further room for improvements. So this is a boring slide. I've presented, I think, 10 times on conferences, but it shows this general procedure of Eurocode. It's a methodology for structural timber fire design. And it is a two-step procedure that is normally done by engineers. And that is the first step, the residual cross-section calculation. And the second one is then calculation of an effective cross-section. So what is now the focus of my presentation is a so-called step 0. So before doing the known steps 1 and 2, we need to talk about the definition of a design fire. And in the majority of the cases, there can be still the standard fire. But for these other 20% I was mentioning before, for larger spaces, for more complex spaces, for taller buildings, we need to talk about the fire scenarios. And there is a lack at the moment of knowledge, education, but also guidance. And I will give you some here in this presentation. Overview of design models. I promise that I will address some at least. And looking at, let's say, evolution of general fire design models, not only for timber and essentially not for timber, we could see this evolution. It started from 1900, where it was not known that there is different fire temperatures. I think there was a very odd number that people assumed, 924 degrees Celsius. That is the fire temperature. But finally, standard fires were found, defined, later on modified to parametric fires. Zone models were introduced, more like for the energy balance solving. Then we found that there could be a localized fire that might be traveling through an open space. My colleague presented some before, Dave. And today, I think the, let's say, top of the evolution is fluid dynamics, which have been found reasonably interesting also for fire. However, when it comes to timber now, we rely very often still today on this ISO EN standard fire. And I will come back to that very soon for one more slide. A more complex design is already the parametric fire design, where you can account for, let's say, the project-specific boundary conditions. And real fire simulations are then considered to be more relevant for more complex buildings. Now, talking about Eurocode work, it was not only writing the Eurocode, but we had also to deal with side topics. And one of these side topics was the applicability of standard fire furnace testing for timber products which are combustible. And that was not an easy task to do, but I can already now tell you, well, it is still applicable. It depends, however, what questions do you want to solve? So until the 1980s, we have tested a lot of linear members, columns and beams. People were very happy with that. But in a, let's say, a bigger environment or a compartment in general, they do not deliver too much to, let's say, they do not contribute to the fire as a larger member would do, like the CLT member, where you have an entire ceiling or a wall exposed. And those elements, they affect the fire dynamics in a compartment, whether it is a room or a furnace, like you see here. So the question was, can we still use it? And the answer was yes, but just for certain things like load bearing capacity, charring, but not for the assessment of the question, does it burn out? Will we expect burnout? And how long will the fire be? And will it be longer? Or will we have external flaming like you see here on this picture? But people were then saying, well, rather do compartment tests. And we have seen a lot of these compartment tests. And looking at these compartment tests, I will later on show you the same graph that Dave showed you. We cannot do always compartment tests because even these tests are probably only one fire scenario, while slightly different ones will lead to other questions. Now, looking into the parametric fire design of Eurocode, it's implemented in Eurocode 1, has a connection to Eurocode 5. So looking at the chart or the graph, you see here already in the background, it's just 20 equations you have to sort together, and you can summarize them to only these elements shown here. And in a direct application, it takes just 5 minutes to calculate this fire, let's say, charring depth for the parametric fire. However, this is not possible and not valid because it's not true that the assumption can be made that structural fuel load is already considered or automatically implemented in these, let's say, in this procedure. An alternative or an improvement would be that you consider the charring depth to the fuel load. And in fact, we will go to that point a little bit later, but I need to speed up. I see my time is running. So the question was, how would a timber member behave in natural fires? And let's have a look at the assumptions we always do and what is the critical points about it. When we have a non-combustible environment shown here, you will have the movable fire load burning, you will have a certain amount of external flame. Now we change some elements in this compartment, we will get an increased exterior flaming, we will have still this movable fire load that I referred to earlier, and we will get some charring, and that volume would contribute or would represent a certain amount of additional structural fuel load. So the question remains here, can we still just put this together and calculate as usual, or can we consider something else, or do we have to consider something else? That's why I put this sign here for the plus. So how can this be superimposed? Yes, we could do a lot of further tests, but we don't have money for that, and neither we have time. You have seen that. Unfortunately, most of the tests are very small, but we want to extrapolate to a very large, let's say, compartments. Looking into literature and existing research, you can find some very interesting points. And one is the first test of a series done at VTT, where Tula found that, interestingly, only a certain share is that you would expect to be, let's say, the contribution to the fire is in fact also measured as total heat release rate. And my colleague, previous colleague and still good colleague at RISE, he was the first one that put down an equation which describes more or less exactly this behavior. So he said that the contribution of structural timber can be described by the charring rate, by an energy release developed by the cone colorimetry, and a so-called fitting factor from compartment experiments. That means that not all of the energy embedded in the timber will be combusted. However, unfortunately, this is strictly speaking valid only for the steady state, fully developed phase. Question is, how can we work with that? And here comes the most, let's say, critical and complex slide with some equations. So taking now this equation from Daniel, we got comments in Eurocode. Well, we fire scientists, we always talk about embedded energy and mass loss rate. So, okay, let's take this one and consider now timber as it really behaves. And that's why I call it combustion behavior. So I invite you now to make a little shift of whatever people told you in the past and add some elements. So people told you that the char layer is so good because it will insulate your wood from the compartment. However, in fact, you always have to consider that this char layer is also an energy source. And by this energy source, you will have a certain contribution to the charring on one side. And on the top side, you have the energy release to the compartment. Meaning we can describe the behavior here by the mass loss, which is a measure of the material conversion from wood to char, and also as a measure of the combustion of the char layer. And if it decays, then we also have decay in our compartment. So getting more deeper into these equations, that means we can describe now the combustion by a certain element accounting for the pyrolysis and the oxidation. Because, I mean, strictly speaking, we could say now quite offensively, timber doesn't burn, it is the char that does burn. So the equation can be now extended, talking about we need to convert wood into wood and char, and finally we combust the char in an oxidative process. And that is now this decay of char layer I was talking about. Now that was quite the theory. Going back to Eurocode, we said, okay, we try to make it very simple. We say the combustion can be described with a constant, and that is derived for wood, structural wood, based still on the charring rate in kilowatts. So we have 120 kilowatts per square meter per millimeter of charring. And then there is this difficult factor to explain. I will do one more slide on that. So the alpha ST value, what is it? We assume we have one material that is wood, our energy source. We have now char, that is our energy storage. In a combustion process, we convert material 1 to material 2. Some of the heat is released directly. The majority is temporarily stored in the char layer and later on released to some extent, a reduced extent or an increased extent. And in fact, this is now the factor alpha observed by Hakkarainen and Brandon and also now implemented in Eurocode. So I worked the last 5 years in developing a model about how we can describe now this combustion of char sticking to timber. In the same time, we want to convert timber to char. And that is described in this timber charring and heat storage model. I have no time to talk about it, but you can click on this link here or look for it on Google, and you will find an open access journal paper. So it allows now to calculate this energy balance between the structure, the compartment, and the exterior. And there we can now describe how this sum works. And I've put down here some figures. So using now a zone model, but it could be also a more complex model, we applied ticks on this model to assess this heat release by the structure. And at the very end, we get this structural heat release rate for the compartment and the products we have. And you see here, we have this alpha factor, and the alpha factor can be simplified. And that is described at the moment by Brendan. And we expect that we can do that also for a lot of compartments and give guidance in Eurocode at the later stage. The alpha factor tends to increase at the very end when you have char combustion, and you will see also this little peak here at 60 minutes. This is when either the walls kick in and we get extra flaming and it does not burn out, or if it burns out when the cooling is superior. So in fact, to some cases, this modification factor can increase above 1. So comparison, I know I'm late, I'm running out of time, but give me 2 or 3 more slides. So parametric fire, I told you the 2004 version does not work. You would get this fire for a compartment. That's test 2 of Daniel. He gave me his results, where you would get a charring depth of 37 millimeter only, which is incorrect. And applying these 37 millimeter now, you would get increased charring and also double the time. And at the very end, and this is when Eurocode model would say it's burnout, you would have 260 millimeter of charring, which is too much, we know, and unreasonably high. Adding an additional and improved charring model already would reduce the charring depth, the prediction, by 170 millimeter. Or to 170 millimeter. And in fact, this model will be or is implemented in Eurocode already in the 2025 version. Looking now at the advanced model I presented earlier or I mentioned, you will see here the ticks present, let's say prediction predicts a value between 60 and 61, 68 millimeter. And also, Daniel did not observe one charring rate. People have to understand that this is a scattered value. We have some charring in the walls. We have some minor charring somewhere else. So you will have a distribution. Looking at all results, this is measurements by Daniel, a mean value of 56. We have the prediction by the TICS model, the wrong implementation of Eurocode existing version, and the iterative approach with alpha 1 and an improved charring model. So as you see, there's a lot to do wrong. And Eurocode, we are aiming at developing these alpha values for certain, let's say, ranges to be applied. Let's say a square meter of compartments, residential use, ventilation conditions. And that should be then, let's say, easy for engineers to implement. However, not to be used for skyscrapers. My conclusions now, last page, slide. So Eurocode model in the existing version does not consider a fire load by structural timber, and therefore no burnout can estimate it. The fire dynamics is a structural and complex, or let's say is a complex area, and it is difficult to cover in standardization. So if you want to go into details, you need to ask specialists. If you want to, let's say, answer roughly, I think it's feasible. Submodels, I did not talk about that too much, but those we see need to be checked if they are valid also for structural timber. Data acquisition in tests, I would like to highlight, and we'll come back to that in the World Conference of Timber Engineering Conference. Eurocode, I can promise, will further develop until it is really published. And yes, that was already the invitation. World Conference, I will talk about fire dynamics. My colleague will talk about data acquisition in compartment tests. And we have also another contribution for the robustness in fire of structural timber building. Thank you very much.
Thanks, Joachim, for this really luminous presentation. So now we should open the chat for questions. Let's see, I do it there. Now, let's see again. And I invite Daniel and Christian to join. I think David have leave us and is taking a sleep. And let's see, first question, will the videos and presentation be shared? Yeah, that's something that we have been thinking about, and we will see where this video will be uploaded. So let's see, we strongly would like to have short questions so that we can take them as quick as possible. And there are some for you, Daniel. Do you see them?
Yes, I see many. Right, I'm just looking at random. It's going quite fast. So did you experience any issues with the joint of the ceiling elements? Yeah, so we noticed that the most important aspect of jointing is actually airtightness, and it's not a new thing, but so wherever the structure was airtight, it worked, and we used sealant materials that had a relatively low temperature. A temperature limit, so a maximum temperature, and the idea was if it's airtight, that there's no hot gases passing the joint, and then this well, the sealant shouldn't get hot. And we know that the best way to seal it is actually to use a more resilient method. Just use either 2 barriers, or I guess what you could also do is implement, but that's what we didn't study. But you could implement fire sealants as well. But I guess that is something that is from other tests in this one. But airtightness is the main thing, and you can achieve it best by having 2 barriers of airtightness.
Pierre, if I may, there was perhaps 2 questions that were raised during David's presentation that were Daniel's presentation that are worth perhaps going back. One was about testing in residential buildings with and without sprinkler systems. Just a quick answer is yes, this has been done through the NFPA projects that Daniel mentioned in his background information. So in the, no, it was done by the American Wood Council, sorry, another series with the US Forest Product Lab. So there were 2 tests out of 5 that were using sprinklers. So we can provide further insight on those. And another question that I will leave, no, that was during David's presentation. Unfortunately, he's out, but that was from Joseph about the crib ignition method. So we'll have to get back to Joseph about that.
Yeah. Let's see.
Well, there is a question regarding reparation. I guess yes. At this stage, it is still ongoing, our reparation project, but so far it seems successful. So what we do after we fix it is that we test the strength after the reparation.
Is it okay for you if you stay here like 5-10 minutes more?
Okay? For me, it's okay. Yes.
Yeah. So then we say that we are here until 10 minutes after schedule. And let's see. Maybe the last question to Joachim. I don't know. Do you?
There would be one for Joachim related to the work.
Yeah, I tried to answer already some, but I cannot write as quickly as I should. Well, 2 questions I see with my name. Question about furnace exposure. Yeah, so the long answer is do some readings about that, and I'm happy to discuss. But what we see from the furnace testing, in furnace testing now we assume standard fire furnace testing, is that absolutely right. There's a reduced fuel needed, and that's what I call now the burner fuel. We use less burner fuel to fire a furnace when we use a timber ceiling compared to, let's say, a lightweight frame structure or a concrete element. 2 reasons. The concrete element will need more energy and will eat up energy and absorb energy. So that is roughly 20% of the reduced energy. And the other 30% of the reduced energy would be the contribution by timber itself. And we did analysis of the char. So make your hands dirty and have a look at the material. So we made analysis of the char after tests, and the contribution by structural timber is between 50 and 100 kilowatts per square meter in these furnaces. So, and what does that mean at the end for the furnace test? Well, not too much. Depends on the question. So in a fully developed fire in a room, just adding more fuel will not mean that it combusts more severe. Yes, it will combust eventually longer, yes, and it will combust exterior, but the room will not get hotter. It's like if you have your fireplace at home, put in 2 sticks, yes, well, that's okay. Put in 4 sticks, well, it doesn't be doubled as hot. The fire will be longer, and that's why we say the duration cannot be assessed. The burnout cannot be assessed by a fire test, and neither the external flaming. But for the fully developed fire phase, the furnace testing is still, let's say, useful. Was that kind of okay for understanding?
I would say yes, yeah. But yeah, maybe Daniel or Christian want to add a comment or maybe pick another question.
Well, I think if I recall also, Joachim, from your studies on the furnace, is that indeed, as you mentioned, indeed, it takes less gas or fuel to fire up the burners. However, the exposure at the surface of the element are the same.
Yeah, but people answer or ask very often, well, just because you have a timber compartment, you do not have half of the sofa. So, which is true, but putting 4 sofas in will not make the, let's say, room significantly hotter. But it will burn longer eventually, and you will have exterior flaming eventually. So, yeah. I think we can close this question from my side.
Good. Yeah.
Yes, could I just add a comment? Well, just reflecting to what was presented today, I think one aspect might not have been mentioned is that I guess there are scenarios that can just be, well, this safety can to some extent be guaranteed with strict prescriptive rules as well. Like you could, I guess most people here would not argue with the fact that if you have significant gypsum boards on all surfaces, you protect all surfaces, let's say with 3 layers of gypsum boards, that in the vast majority of fires, but by far the vast majority of fires, that there wouldn't be an issue. And then I guess if you expose a bit more, you will, it will be adjusted. But there could be a list of prescriptive rules that guarantee safety instead of solely focusing on performance-based design, because performance-based design has a disadvantage that you need an expertise to do it, and that can go wrong more easily than using prescriptive design. Well, I guess we need an increased expertise. That's the right way to say it.
Yeah, and I think what is also needed is we have some severe fires. In fact, we have some, and we expect also accidents in the future. And a very good example is the Swedish fire that led to a loss of a building. However, that was properly analyzed. So we could analyze and trace back what were the faults. And the building regulations and also prescriptive code elements, Daniel, Daniel referenced to, we know that they are the result of tradition and experience. So we need to gain experience. And that's why if there is a fire, we need to analyze what was wrong, what went wrong, where are the critical elements. And those who were, let's say, aware of the most recent fire in Tyrol Motorcycle Museum, I expect very soon an analysis going on to show what was the problem, where are the assumptions you should not take. And the same with David's test, very valuable. What is the impact to our, let's say, design? What's allowed, what's accepted? Can we address that with models, or do we need to encapsulate a certain share?
Pierre, do you think we should round off the meeting?
Yeah, we just say we can keep until 10 minutes after schedule. So maybe 2 or 3 minutes. If I see their question, I don't know if it's out of scope or it's regarding firefighting. And I see several of them. Do you have something that you could say about that? I know that you are focusing on this fire dynamic, and so how?
So after art tests, you mostly had smoldering, like some hotspots, and it was quite experimental. We extinguished it with water mist, or I guess cooling down is sometimes a better word, but yeah, we use water mist as an alternative to just water, and we used somewhere in between 40 and 160 liters of water, which is significantly less than usually is used, even if it's a less significant fire, because we practically extinguished, especially in the ceiling. So we did some experiments. What is important is you don't see smoldering fires. You don't see them with your eyes. You need to see it with a thermal camera, and I think more studies have looked at that.
Any comments, Joachim or Christian?
Well, I would like to highlight one chapter of Eurocode. I think I did that to some extent, but we see that especially the smoldering and glowing combustion is a topic, and we try to address that, or let's say it is addressed by detailing. That means at least proper detailing would allow for a reduction of these risks. That means, as a rule of thumb, no path through, let's say, construction, reduction of voids to a minimum, and so on and so on. Foresee some movement, openings, changes in joints, and also foresee then measures to account for that. And that can be just simple mineral wool, that can be standard sealant. It does not necessarily mean that you use always the most expensive fire-rated product. If you do smart detailing, you help the building a lot to reduce smoldering and glowing combustion.
Yeah. Maybe I think I can add a final question. Now we have been listening to experts from the different regions around the globe, and I wanted to have your feeling, or my feeling was that it started to be quite standardized the way we are working. I'm not an expert in fire. I'm looking at when it's cold, but concerning this topic of fire safety in taller timber building, do you feel that we're working more globally as in the same way, or are there still some big differences, cultural or others?
I can start answering on this one. I found that indeed in the past few years, there has been some sort of more harmonization, I would say, and collaboration internationally. Like Joachim was referring to the cost action that gathered a lot of fire researchers around the globe, so not just Europeans. There has been and still are a lot of work being done throughout many countries collaboratively, which is great. And we keep regular discussions, I would say, among all of us to make sure that we don't necessarily duplicate the work, and we capitalize on all of the outcomes that one got, so that we don't make the same mistakes, I would say, and try to identify and generate new data.
Mm-hmm.
And we should continue.
Yeah, I think so. All right. Any more comments? Oh, I think we can end this webinar. So then I would like to thanks again David, Daniel, Christian, and Joachim, and all you participants for having the passion to write your question only there in the chat. So also I would like to thank Sylvain Gagnon at FP Innovation and Jean-Luc Kojumji at FCDA for their support during the organization. And if you are interested in seismic, then follow our next WoodRise webinar that should be held in September, I think. And if you're interested in timber buildings, a bit more in general, but even in detail, so you should not miss this third WoodRise Congress in Kyoto, in Japan, the 15th to the 19th of October this year. And then maybe we might meet, hopefully, face to face. So thank again, everybody.
Yes, thank you, Pierre. Thanks also to you for hosting this.
Thanks.
It was a pleasure.
Yep.
Okay, keep safe. Goodbye and good night, maybe. Bye-bye.
Thank you.
Thanks. Bye.